All right, I'm going to do an additional little exercise here with you on how to do chi-squared. A little bit of confusion on how to do this. So I created this little sheet here that has, and I guess I can post this on the OneDrive, but the idea here is this is a definition of how to calculate the degrees of freedom and to actually find what I call the magic value. And we'll talk about exactly what this magic value is in a second. But if you look back on our PowerPoints, we had a problem like this. And in this, it said there were 3 degrees of freedom. Now, what does that mean? Well, it has to do with how many variables are interacting with one another. And you calculate this number of degrees of freedom, at least in the problems that we do, like this. All right, you read this, it says degrees of freedom, that's df, equals r minus 1 times c minus 1. Well, the r are the number of rows and the c's are the number of columns. So we look back on our problem. All right, now that's still not easy because, hey, look, 1, 2, 3, 4, 5, 6, 7. We've got, 7 columns and 5 rows or what. So which ones do I actually column? How did they get 3? Well, it's how many numbers you actually have going in, how many variables. In other words, in our particular case, we have 4 variables along here, and then we have 2 values for each of those variables. So for us, what we do is we're going to have 1, 2, 3, 4 rows and 2 columns. So if you calculate that using our little formula that we come up with, one is 4 and the other one is 2, that is going to be 4 minus 1 is 3 times 2 minus 1 is 1. So it's 3 times 1, and so the degrees of freedom are 3. So what we do, we come back, oops, wrong one. That's where I went and got this. So our degrees of freedom are here. Now, in statistics, you get to choose how stringent your statistics are. So how often are you allowed to fail? How often can the statistics get it wrong and you still feel comfortable about it? Well, and that's a choice, and that's how some people kind of maybe cheat in statistics. Maybe they'll raise this to an even higher number. Generally, we say, well, if you get it right 95% of the time, that's good enough. But there are some things where you want to get it even more accurate, and you want to get it 99% of the time correct. And then there are people who are very strict and want to get it 99.9% time. So this is basically 1 minus that 95%. That's a 0.05. That's your p-value. All right, that's your cutoff threshold. So it's not a value. It's kind of saying, how often do I think it's okay to get this wrong? If, in other words, the numbers are wrong, how often if I get a value like this, how often is that going to be correct? Well, if it's going to be correct 95% of the time, okay, I'm okay with it. But maybe I want it to be 99% of the time, so I would use this value. And if I want it to be 99.9% of the time, they do it over here. At NASA, for instance, I have a friend who works at NASA, and they do what's called 6 sigma. And 6 sigma means that you go 6 digits beyond here, and they only get it wrong, 5 zeros and a 1. So that's 1, I can't even calculate that, but that would be 0.000001 amount of the time. So that's like 1 in a million, I guess. So the idea is when they do their statistics, they're very precise. In biology, where you're dealing with living things, we don't have to be that precise. If you were, you would have to be crossing flies for a year to do one experiment, because you would need like several million flies to get that level of precision, and so you'd have to be doing this experiment forever. But that they can do that there, we can't do that. So here you would run, maybe you have several hundred or even several thousand, and 95%, that's probably fine. So we choose, what number do we choose? Well, if we only had one, I know I did an example for you using Hardy-Weinberg in one video, and we chose this one because that's the number of rows, and we had 2 rows and 2 columns, And so that was 1 and 1. 1 times 1 is 1, so we only had 1 degree of freedom. In this particular case, we have 4 rows and 2 columns, so that's 3 times 1, 3. So we have 3 degrees of freedom, and if we're good with 95% of the time, then this is what I call our magic number. This is our threshold. And what this does is that this is basically a number that says, how much change is there? You look at chi-squared. Chi-square is a measurement of change. And or maybe you could even look at it as variability. How far away can we get from the expected value, the value I think we should get, all right, and and be able to say, okay, that's close enough that we don't have to worry about it just being randomly there. So what we do is, if you go above 7.815, all right, if you're above 7.815, then you have changed a lot. All right, you have changed so much that we no longer think that this is following the model or the way you believe it. If we are below it, all right, below 7.815, we believe that nothing has changed. Everything is exactly as it was. Now, how do we interpret that on our chi-squared? Well, what we're doing, we're comparing these two numbers. And we're looking at 2,449 and 2,490. And what we're saying is there's a change. We expected this, and we're saying, is this close enough, all right, for me to say that these are actually okay? They're within 95% of the time. This is close enough to say they're the same value. And the same with all of these. And so you can combine all of your answers into one number that says how much change was there, and whether or not your model, that's the expected more or less, fits the observed data. Mendel says we should get this. This is what we observed. Chi-square tells us that, well, 95% of the time you would be correct if you said that your observed data fit your model. 95% of the time. That is, if what? If you come in below 7.82. Well, when we calculated this, we ended up with a number of 4.57. That is below this magic number, 7.82. So what we're saying is the p-value says that 95% of the time, this is a correct answer. In other words, we would state this as we fail to reject the null hypothesis. Now, what does that mean? What is the null hypothesis? Well, the null, obviously, we were below it, and we failed to reject the null. So what was the null? If we failed to reject it, then we must have more or less accepted the null hypothesis. All right, so think about the way this is worded. You did not reject it, so you accepted it. And what was the accept? Then what did you accept? Well, we accepted that these two are the same number. All right. So in other words, our null hypothesis was that the observed and the expected were the same. Well, what does that also mean? It means your original hypothesis is what? All right. Well, up here it says the UN is located at this. So what we're doing is we're saying that UN is located here, 37 away from the chromosome. So what we're doing here is, by saying that these are reasonably close, that this is indeed a correct answer. I know that sounds horrible. It almost doesn't make sense. All right, so you failed to reject your null. This is the proper wording. This is how statisticians and mathematicians say this, and it gets confusing. But because we were less than this number, we're actually saying these are the same, and we are failing to reject the null, and therefore we are accepting the null, and the null is saying that this is located at this particular place. That's the way you say this. All right, so I know it sounds confusing. It takes a while to get used to how to state your hypothesis and your null. All right, because of course, your hypothesis then, if this is your null, your hypothesis is the opposite of this, and essentially your hypothesis is that it's not located there. And it's you do this way, and it's kind of the way you can cheat with statistics very easily is by just subtly changing your hypothesis and your null hypothesis, and usually people don't notice it. But if you're doing with this type of analysis, this is a common type of analysis, somebody would catch it. But in another type of experience, I find it all the time where it's very subtle, and you read it and you go, "Oh, these statistics are just hooey." I don't know a good word for what I would say when I see someone do this, and I see it all the time, especially in medical journals. I see a lot of stuff online these days in COVID where they have just subtly changed the wording of their null hypothesis, which just completely makes these meaningless. And yet they did it. They said it that way, or they said it wrong, and it just makes no sense. And this is a very common thing. I saw a statistician go through one whole year. I think it was like the year 2014, and he went through one whole year of all the medical journals in all the major ones anyway, something like 2,000 journals. Went through every article that stated a hypothesis and a null to see if they did it right, and only 40% of them did it right. So that's pretty scary, and that's in medicine. All right, so there's my statistics lecture. Let's just say that people lie all the time, or at least they get confused a lot. That's maybe the more polite way to say it. And they do. It's easy to get confused on what's going on here. I have to think about it like 5 or 6 times. I have to go over it in my head to figure out what's going on, especially when you state it in really confusing ways, like fail to reject the null. So these are all, it's like a triple negative: fail, reject, and null. All right, that, you know, if it were English, you would say this is totally wrong, right? But this is the way mathematicians and statisticians word these things. So I hope this makes sense to you. This is why we used 7.82, and your value here when you come up with this is 4.57, and that is less, right here, 4.57 is less, and that means that you failed to reject your null if you worded your null this way. All right, if you word it this way, then a number lower than the magic number here that we looked up on the table, that will be a fail to reject. All right, which is kind of an accept. But you don't ever accept it. Now, I also want to make sure that you never say you proved anything. I want to very much emphasize that statistics never prove anything. All right, they simply either fail to reject, all right, or they reject null hypotheses. They don't prove hypotheses. They don't reject hypotheses. Everything is based on the null. You fail to reject the null, or you accept the null. I'm sorry. Or you either reject the null or you fail to reject the null. You really shouldn't say accept. Some places will say you accept the null instead of fail to reject. But this is the correct wording. All right, I hope that helps a little, and hopefully if you take a psychology class, a lot of times they will do this in, certainly a statistics class will do this, but you'll find this in a psychology statistics class. That's the place you'll get this, and statistics, and of course, in genetics.